In the world of interior design, lighting and color have the power to elevate a space or leave it feeling flat. Often overlooked, these elements play a crucial role in shaping the overall experience and well being of the occupants. Have you ever chosen a color from the swatch book and it appears completely different on your wall? Or
Imagine walking into these rooms. How does it feel? Does it invite you to be in the space? Instead, imagine walking into these rooms. How do you feel? Secret? Magic of color and lighting. Welcome everyone to Design with Colors. Today, on a lightning show, we are exploring the power of color in interior design. So, how much power does color have? Color has the power to completely transform a space, set a mood, influence emotions, reflect your unique style. We will be exploring
The psychological effect of lighting, the color psychology, how we perceive the dynamic range of colors, and the energy consumption of lighting fixtures.
ever wonder why certain rooms feel calming while others feel energetic? It's all about color. Warm colors like red, orange, and yellow boost energy, making them great for kitchen or living areas. Cool colors like blue and green promote relaxation, perfect for bedrooms or bathrooms.
colors can have an impact on the productivity of the occupants. Study by the University of Texas found blue environments can even increase the productivity by creating a calm, focused atmosphere.
By deciding how to paint all six walls in a room, we can simultaneously alter and influence our perception of space. So, next time you paint a room, consider the mood you want to create.
Let's discuss the physiological aspects of lighting. Consider two bedrooms, one with cool lights, other with warm lights. Which lighting do you think would be good for your sleep? To explain this, we need to understand what is circadian rhythm. Circadian rhythm is a natural internal process that regulates our physical, mental, and behavioral changes over a roughly 24-hour cycle. It regulates sleep wake cycles, hormone production, and alertness. Exposure to sunlight during the day suppresses melatonin levels or the sleep hormone and keeps us energized. As the night falls, natural light diminishes, triggering melatonin production, preparing us for sleep. So, how does the internal room lighting affect your sleep? To understand this, we need to understand the color temperature of the lights. According to the theory on correlated color temperature, warm yellow light promotes relaxation, whereas cool blue light helps us to focus.
Hence, warm light in the evening mimics the sunset, signaling our bodies to take rest.
Whereas bright blue light during the night can disrupt our natural sleep cycles. Bright blue light is essential during the morning. It also interferes with cortisol and serotonin production. Less exposure of these hormones can lead to mood disorders and fatigue. But cool colors help with relaxation, right? True. This debate over blue color's ability to promote relaxation versus warm color's effect on the sleep cycle has boggled lighting scientists for decades.
Okay, now let's discuss the energy consumption. We are sensitive to different wavelengths. Ignoring the color of light, if a light has only 555 nanometers, it would be most efficient as all of it would contribute to its brightness. The light we usually use has a mix of wavelengths. There would be portions of light that would be less efficient or waste based on their wavelengths. This is the entire electromagnetic spectrum of the light source. The total power in the visible spectrum, also known as the radiant intensity, is given by this formula. Note that this power is in watts. This is the visual efficiency function. Let's assume this is the latest one. This is the power of the light that we can see. The area under this curve gives us the brightness of the light, given by this formula. Note that this power is in candela. The ratio of luminous intensity to radiant intensity gives us the luminous efficacy of radiation. Note that this is the efficiency of the radiation for vision and not the efficiency of the lighting fixture. The luminous efficacy of radiation gives us the visual efficiency of the radiation, whereas the efficiency of the lighting fixture is the ratio of visible light output in lumens to the total energy consumed in watts. Look at the LERs of the lights in Wilkinson building. We observe some CFLs have better LERs than the LEDs. This means that these CFLs have better radial efficiency. This may or may not translate to their energy efficiency, as we do not know how much electricity each of these lighting fixtures consume.
Coming back to the mismatched color, let's see why this happens.
The answers lie in the spectral power distribution of lights. Comparing the LEDs, we found that CRI is not really related to color temperature. Generally, LEDs with low CRI have these peaks and dips which were more pronounced than the LEDs with higher CRI, as you can see. It is possible to have multiple peaks and dips which will contribute to the energy efficiency as we discussed earlier and still have good CRI.
High CRI lights make the wall colors look more accurate than the same wall color seen in low CRI light. This is important in spaces where true colors matter.
In the absence of light, we cannot interpret the color. We perceive the spectral power distribution of the reflected light from the object as the color of the object. Let's assume that we have selected azure blue for the wall. The spectral reflectance factor of this color looks like this. Plotting the A star and B star on the CIE color lab coordinates for the LEDs as shown before, we see that the wall will appear in so many different shades of blue based on the LEDs used. Note that we have only plotted the hue and not the lightness of the color. We can compare how this color looks under various light sources. A lighting designer would look at the delta E between all the lights and compare it with the daylight. What is delta E? Delta E is a measure of perceptual color difference of one color under two light sources. Delta E between 1 and 2 might just be noticeable, but delta E above 5 is easily distinguishable and the colors would look quite different for most people. If it is important for this color to look similar under sunlight and at night, you might want to use LED 11.
If you have to use multiple LEDs in a space for different functions, you may want to compare their colors. This is important as different colored LEDs may not be aesthetically pleasing. A lighting designer would use delta U prime V prime to analyze this. Delta U prime V prime represents the difference in the chromaticity coordinates in the CIE 1976 chromaticity diagram.
We compared the colors of the same LEDs from before. These are the delta U prime V prime comparison of all these LEDs. Based on this chart, a lighting designer can make an informed decision of using the different LEDs instead of just using the correlated color temperatures. Comparing these LEDs with the spectral power distribution of D65, a proxy for daylight, we find that LED 11 has the closest color. This can make a good task light for areas that require focus based off our discussion on physiology and psychology.
So, how will you utilize this knowledge? Depending on your budget, you may want cheaper light fixtures with acceptable CRI and desired color temperature to fill your room if accurate color reproduction is not important. Some special lights with high CRI can be used to highlight certain elements for task specific activities that require accurate color production. And similarly, accent lights can be incorporated to set the desired mood of the space.
Apart from CRI, you will select the wall color according to the mood of the space and select appropriate lighting based on the utilization and function. When there is a clash of function, you may want to use multiple lights or use lighting with an adjustable color temperature. A good interior design is about how we connect these dots and how we balance it against the cost.